Tonight, we are going to look at the most successful theory in the history of science. It has been tested more than any other idea humanity has ever produced. It has passed almost every direct test of what it was built to predict. It predicted particles years before anyone could build the machines to find them. It described forces invisible to the human eye with a precision that still seems impossible. And it is already confirmed wrong. Not suspected wrong. Not arguably incomplete. Confirmed by a Nobel Prize winning experiment to be wrong about something it claims to explain. The evidence has been sitting in the open since 1998, and the framework still has no way to fix it. That is just the first problem. There are more: experimental, mathematical, and cosmic. Each one found by a different team, in a different country, using a different machine, over a different decade. None of them connected. None of them planned, each one arriving independently from a different direction, pointing at the same conclusion. The theory that describes everything we know about matter and force, the theory that explains every atom in your body and every particle of light hitting your eyes, is not complete. And the machine that was built to find out what is missing has just delivered its final Run 3 dataset before the high luminosity upgrade. The data is already there, sitting on storage drives in Geneva and across computing centres around the world. The Run 3 dataset may already contain the next clue, something that strengthens a pattern, dissolves an anomaly, or narrows the space where new physics can hide. The answer may not arrive as one clean discovery. But the next boundary of the standard model is being measured now. Tonight, we go inside what they are looking for. Before we get started, if stories like this make the universe feel larger and stranger than it did before, take a second to subscribe. It helps this channel reach more curious minds like yours. Now, let's begin. Here is the first thing you need to understand. There is a chart. One chart. It fits on a poster smaller than the ones in a school hallway. And on that chart sits everything we have ever confirmed about the building blocks of the universe. Every particle ever detected, every force ever measured, every fundamental interaction ever tested. One page. Physicists call it the standard model. It is not a simple list. The mathematics behind it spans entire textbooks. But the core idea is contained in a single diagram that any scientist in the world can recognize instantly. And for 50 years, that diagram was in effect unbeaten. The standard model was not just a good theory. It was the most precisely tested idea in the history of human thought. Then, one by one, in different rooms, on different continents, using different instruments, things started coming back wrong. Not dramatically, not with explosions. Quietly, stubbornly, in the way that a crack in a wall appears first as a hairline, then grows wider no matter how many times you paint over it. And these were not cracks found by people looking for problems. They were found by machines designed to confirm the theory was right. By experiments built to verify, not to challenge. By physicists who trusted the framework and were surprised when the measurements returned something the framework could not contain. That is the story of tonight. Multiple independent failures in the most tested framework in science. Some of them experimental, measurements that come back wrong. Some of them mathematical, predictions built into the theory's own equations that are catastrophically off. Some of them strategic, entire theoretical candidates that have been searched and not found. the standard model works beautifully. And it is not complete. Tonight, we are going to follow every failure to its source. By the end, you will understand why the next clue may already be sitting in data collected weeks ago, and why the scientists reading it right now are doing so in a quiet that feels different from any quiet in the last 50 years of physics. July 4th, 2012. A crowded auditorium at CERN. A slideshow. A graph with a bump in it. The bump was the Higgs boson. 50 years after it was predicted. After decades of searching. After the construction of the most powerful machine humans had ever built. The particle had been found, exactly where the theory said it would be. The mass that was measured, 125 billion electron volts, sat precisely in the range the standard model allowed. Not at the bottom of the allowed range, not at the top, but somewhere in the middle, with no special significance other than the fact that the equations had been pointing here all along. Some of the physicists in that room had spent their entire careers on this moment. Peter Higgs, the British physicist who had predicted the particle in 1964, was present in the audience. He was 83 years old. When the result was announced, he reached for his handkerchief. At the podium, the physicists who had led the two main detector experiments, CMS and Atlas, took turns presenting their results. Both experiments had independently found the same signal, at the same mass, at a statistical significance that satisfied the 5 sigma discovery threshold. The moment was real, the celebration was real. After half a century of theoretical confidence and experimental hunting, the last missing piece of the standard model had been found. And it was supposed to be the beginning, not the end. Here is what most people do not know about that moment. When physicists found the Higgs boson, they were not expecting to stop. The Higgs was the last confirmed prediction of the standard model, but the standard model was also known to be incomplete. Finding the Higgs was supposed to open a door. On the other side of that door, every major theory in physics predicted something else. Not one thing. A zoo, an entire population of new particles that should have appeared at similar or higher energies, supersymmetric partners, heavier counterparts to every known particle, dark matter candidates, new force carriers, new structures of matter nobody had named yet. The theory said they should be there. Several independent theories said they should be there. The LHC was designed partly to find them. So after the Higgs, the machine kept running. From 2015 to 2018, the LHC ran at the highest collision energies ever achieved by any machine in history. Every collision was a probe. Every dataset was a search. Thousands of physicists poring over the wreckage of trillions of particle collisions, looking for something that wasn't in the standard model. They found nothing. Not approximately nothing. Not almost nothing. Precisely nothing new. That sounds like a failure. It was not. It was a result. And it was not the result anyone expected. The leading theoretical extension of the standard model was called supersymmetry. It had been developed over decades. It was mathematically elegant. It solved multiple problems simultaneously. The hierarchy problem, the dark matter question, and others we will return to later in this documentary. Thousands of papers had been written about it. Physicists had dedicated careers to calculating where its predicted particles would appear. The LHC was supposed to find them. To understand what supersymmetry predicted, you need to know that it proposed a partner for every known particle. Every quark would have a heavier partner, called a squark. Every electron would have a partner called a selectron. The lightest of these partners, stable, neutral, invisible to light, was predicted to be dark matter itself. The theory was beautiful. It solved problems that had no other solution. And it made a clear prediction. These partner particles should appear at energies the LHC could reach. The LHC reached those energies. The partners did not appear. Think of it this way. You have a map. The map says there is a city 300 miles north. You drive 300 miles. You drive an extra 100. You drive 200 more. No city. The absence of the city is information. It means the map was wrong about what is north of you. The LHC drove north. And north was empty. Physicists gave this a name. They called it the desert problem. The landscape of particle physics beyond the Higgs, the territory the theories said would be full of new structure, turned out to be, as far as the most powerful probe ever built could see, empty. Entire classes of theories were eliminated. Specific predicted particles, ones that theorists had named, assigned properties to, and built entire careers around finding, were ruled out. Not found and rejected. Simply not there. The simplest versions of supersymmetry required partner particles at energies the LHC had now surpassed. Those partners did not appear. This was not a small setback. It was a restructuring of what physics thought it knew about the next layer of reality. For some physicists who had spent decades building supersymmetric theories, it was the equivalent of being told the map was not just slightly wrong. It was wrong about what the landscape looked like. The confidence that had built up over 30 years of theoretical development had to be put down and re-examined. And yet, the desert itself was strange. The absence of new particles at the energies the LHC probed raised a question that nobody had a clean answer for. If the new physics is not here, where is it? Is it at higher energies the LHC cannot reach? Is the theory pointing in the wrong direction entirely? Or is something wrong with how the theories were built? Those questions had no answers in 2018. They still do not have clean answers now. This is where the story of tonight really begins. Not in 2012, when the Higgs was found. In 2018, when the search continued and found nothing it expected. The absence of supersymmetric particles did not just eliminate one theory. It forced a harder question. What if the next layer of physics is not beautiful in the way theorists expected? And in different places, things were already coming back wrong. In the mid-1990s, a team of physicists in Brookhaven, New York, began designing an experiment around a single question. The muon is a particle that behaves like a heavy cousin of the electron. Same electric charge, same interactions with the fundamental forces, but roughly 200 times heavier. In most respects, the standard model treats the muon and the electron as identical, except for that mass difference, which makes the muon a perfect precision tool. Any deviation from prediction shows up clearly against something that should be predictable. The property they wanted to measure was the muon's magnetic moment. Specifically, a tiny correction to that magnetic moment, called G2. Here is the simplest way to picture it. A spinning charged particle in a magnetic field slowly wobbles, like a gyroscope tilted at an angle. The rate of that wobble is determined by the particle's magnetic moment. The standard model calculates the exact rate for a muon to more than 10 decimal places. That calculation is one of the most precise theoretical predictions in science. Matching it in experiment meant building something extraordinary. The Brookhaven team spent years constructing a 50-foot ring of superconducting magnets. A precisely tuned magnetic field filled the entire interior of the ring. muons were injected and circled hundreds of thousands of times, while detectors recorded every detail of their wobble. The goal was simple to state and extraordinarily difficult to achieve: measure the muon's spin rate precisely enough to see whether it matched the prediction. When the results came in, it did not match, not by much, less than 1%. But in particle physics, that margin is enormous. The discrepancy sat far enough from the prediction that random statistical error could not explain it. Something was off. The team published their result. The physics community did what it always does with unexpected results. It waited for more data. More data arrived. The discrepancy stayed. Then something unusual happened. Instead of fading, as many previous anomalies had, it attracted an institution. Fermilab, outside Chicago, decided to recheck the Brookhaven result by building a new, more precise version of the experiment. The logistics were extraordinary. The original 50-foot magnet ring travelled by truck and barge from New York to Illinois, requiring police escorts through multiple states. The ring arrived. The experiment was rebuilt. Years of data collection followed. In 2025, the muon G2 collaboration released their third and final measurement. It reached a precision of 127 parts per billion, better than the experiment's original design goal. The result agreed with the 2021 and 2023 measurements. The muon's behaviour still does not match the standard model. But here is where the story becomes something more complicated than a simple wrong result. The standard model's prediction for the muon's magnetic moment is not a fixed number copied from a reference book. It requires calculation. And in recent years, physicists realized that two different methods of doing that calculation give different answers. One method builds the prediction from experimental data on electron-positron collisions, using decades of carefully gathered measurements to construct the theoretical number piece by piece. The other method, called lattice quantum chromodynamics, calculates the result directly from the fundamental equations of quantum field theory, using powerful computers to simulate the quantum interactions involved. These two methods disagree. If the lattice calculation is the correct approach, the gap between the measurement and the prediction is smaller than it first appears. The anomaly may shrink or disappear as the lattice calculations become more precise. If the data-driven calculation is correct, the muon is genuinely behaving in a way the standard model cannot explain, and something unknown is nudging the result. Right now, no one knows which approach to trust. The theoretical community has not resolved the disagreement. Papers are published on both sides. The debate is ongoing. 2 machines. 2 decades. A discrepancy that survived both, and a prediction 2 theoretical methods cannot agree on. For more than 20 years, the muon has been the most carefully watched particle in physics. That careful watching is about to matter. Because while the muon anomaly was slowly accumulating across 2 continents, something faster and sharper happened in 2022. A particle sitting at the very foundation of the standard model was measured. The result was not slightly off. It was 7 standard deviations from the prediction, and it did not come from an obscure experiment. It came from one of the most careful precision measurements in the history of collider physics. The W boson is not an exotic particle. Every beta decay in every atomic nucleus on Earth happens because of the W boson. It has been measured hundreds of millions of times. Its mass is one of the most established quantities in particle physics. In April 2022, the CDF experiment at Fermilab published a measurement of that mass. The analysis involved hundreds of physicists and took nearly a decade. The result placed the W boson's mass approximately 77 MeV above the Standard Model's prediction. 77 MeV sounds like a small number. In particle physics, it is not. When expressed in units of statistical uncertainty, the CDF result sat 7 standard deviations away from the predicted value. In particle physics, a 5 sigma result is the threshold for a formal discovery claim, meaning the probability of a random fluctuation producing that result is less than 1 in 3 million. 7 sigma is considerably beyond that threshold. It is not the kind of discrepancy that gets explained by a calibration error or a rounding issue. If the CDF result is correct, the W boson does not weigh what the Standard Model says it should. And if the W boson is wrong, the foundation of the theory that predicts it is cracked. But here is the problem. Other experiments measuring the W boson mass did not confirm the CDF result. Measurements from the Atlas detector at CERN and from other collaborations returned values closer to the Standard Model prediction, though not all fully consistent with each other. The CDF measurement and the other measurements do not agree. This created a situation that is genuinely uncomfortable for the field. The world's best precision experiments, measuring the same particle with similar levels of care, are producing incompatible results. Either the CDF result contains a systematic error that no one has been able to identify after years of scrutiny, which would require explaining how one of the most careful measurements in collider history got so badly wrong, or the other experiments contain errors, or the Standard Model prediction itself is wrong. None of these options is comfortable. All of them have been investigated. None of them has produced a clear resolution. Think of 5 precision clocks placed in the same room. 4 agree within fractions of a second. The 5th says the time is 7 minutes later. You cannot simply say the 5th is wrong. You have to understand why. That investigation is ongoing. 3 possibilities exist. CDF made a subtle undetected error. The other experiments have a systematic bias. Or the Standard Model value is wrong. No resolution. The W boson mass is not settled. The world's best particle physicists, using the world's most precise detectors, have produced a disagreement they cannot fully explain. The Standard Model sits at the center of that disagreement, untouched and uncorrected, while the experiments try to figure out what is happening. 2 anomalies now, 2 open questions, 2 separate experiments, in 2 separate countries, finding 2 separate things that do not fit. But both of those are still, in principle, questions that might resolve, measurements that more data or better analysis might clarify. Open questions, not confirmed answers. The next chapter is different. The next problem is not a question, it is an answer. It has been confirmed by a Nobel Prize for nearly 30 years, and the Standard Model still has no way to fix it. In a mountain in Japan, 1,000 meters underground, there is a tank the size of a 15-story building. It is filled with 50,000 tons of ultra-pure water. The walls are lined with thousands of golden light sensors. Each sensor is designed to catch the faintest possible flash of light. The tank sits inside the Mizumi mine in Gifu Prefecture, chosen specifically for the depth of rock overhead. Rock that filters out almost all cosmic ray particles that would otherwise create noise indistinguishable from the signals the physicists are hunting. Neutrinos interact so rarely with matter that even 50,000 tons of water is nearly transparent to them. Most neutrinos that pass through the tank leave no trace at all, but occasionally, rarely enough that the experiment needs months to accumulate meaningful statistics, A neutrino bumps into a water molecule hard enough to create a charged particle that travels faster than light moves through water. When that happens, it produces a cone of blue light called Cherenkov radiation, a faint glow in the darkness. The sensors on the walls catch it. The structure is called supercamioconde, and in 1998 it confirmed something that the Standard Model says is impossible. The Standard Model does not say neutrinos have approximately zero mass. It does not say they probably have no mass, or that their mass is too small to measure. It says they have exactly zero mass, as a structural requirement of the theory. The mechanism that gives particles their mass, the Higgs field, cannot give mass to a neutrino. The equations forbid it. Not as an oversight, as a consequence of the theory's own architecture. In 1998, supercamioconde confirmed that neutrinos change type as they travel. A neutrino produced as an electron neutrino can arrive at a detector as a muon neutrino or a tau neutrino. This transformation is called neutrino oscillation. Neutrino oscillation is only possible if neutrinos have mass. Both things are true. The Nobel Prize in Physics for 2015 was awarded for the discovery of neutrino oscillations and the proof that neutrinos have mass. The Standard Model has been factually wrong about the neutrino for nearly 30 years. This is not a contested claim. The Nobel Committee agreed. Now here is the part that makes this more than a footnote. If you want to fix the Standard Model to accommodate neutrino mass, you cannot simply adjust a number or add a correction term. The Higgs mechanism, the system that generates mass in the theory, is structurally incapable of producing a neutrino mass. You would have to add new physics. New particles, a new mechanism, something outside the framework the theory currently contains. Several proposals exist. The most studied involves a new type of neutrino called a sterile neutrino, a particle that does not interact through the weak force at all, making it invisible to all standard detectors. If sterile neutrinos exist, they provide a mechanism called the seesaw. The heavier the sterile neutrino, the lighter the ordinary neutrino becomes, in the same way that a seesaw tips when weight is added to one side. If the sterile neutrino has a mass at a very high energy scale, the ordinary neutrino's mass would be naturally tiny, explaining the extreme smallness without fine-tuning. The mathematics of the seesaw is elegant. The sterile neutrino has not been found. And there is a second puzzle inside the first. Why is neutrino mass so many millions of times smaller than any other particle? Nearly 30 years since the confirmation. The framework has never been updated. The mechanism has not been found. This is not a crack in the wall. This is a section of wall that was already known to be missing, and the structure has been holding itself up around the gap ever since. The muon anomaly may resolve when the theorists finish arguing about their calculations. The W-Boson disagreement may resolve when more precise measurements accumulate. But the neutrino's mass is not a question that might resolve. It is a confirmed answer that has no home inside the theory that is supposed to contain it. That changes the question of this documentary. It is no longer, is the Standard Model incomplete? It is confirmed incomplete. Has been since 1998. The question is, how incomplete? Where else has it been wrong without anyone noticing? And how many of the separate anomalies building up across different machines point to the same missing piece? The neutrino was the first confirmed gap. The next gap is not in a particle that behaves wrong. It is in an entire category of matter that should make up nearly a third of the universe's energy, and that no experiment on Earth has ever directly detected. Every galaxy in the observable universe is held together by something invisible. Not metaphorically invisible, physically invisible. Something that does not emit light, does not absorb light, does not interact with light in any way that any instrument has ever been able to detect. And yet it is there. Its gravity shapes every structure in the cosmos larger than a star system. If you map the rotation of a spiral galaxy, measure how fast stars at the edge orbit compared to stars near the center, the numbers do not work. The stars at the edges move far too fast. If the galaxy only contained the matter you can see, the outer stars would fly off into space. They do not fly off. Something is holding them. That something is called dark matter. And the evidence for its gravitational effects is not controversial. It shows up in galaxy rotation curves. It shows up in gravitational lensing, the way massive objects bend light from objects behind them. It shows up in the large-scale structure of the universe, in the way matter clumped and clustered after the Big Bang to form the cosmic web of filaments and voids we see today. Every major cosmological model requires it. Without dark matter, the universe does not look the way it does. So physicists went looking for the particle. For decades, the leading candidate was something called the WIMP, the weakly interacting massive particle. It was not invented arbitrarily. It emerged naturally from a theoretical framework called supersymmetry, the same framework that predicted partner particles the LHC searched for and did not find. The WIMP was appealing for a specific reason. A supersymmetric theory naturally produces a heavy particle, stable, electrically neutral, that interacts with ordinary matter only through the weak force. If you calculate how many of these particles would have been produced in the early universe and survived until today, the number matches the observed dark matter density almost exactly. The agreement felt like a sign. Physicists called it the WIMP miracle. The theory produced the right abundance of dark matter without fine-tuning. Physicists called it the WIMP miracle. The theory produced the right abundance of dark matter without anyone fine-tuning the numbers. Two separate kinds of experiments went looking for WIMPs. The LHC searched for them directly, trying to produce them in collisions and detect the energy that went missing when they escaped. Underground detectors, shielded from cosmic rays by kilometers of rock, waited for a WIMP to pass through and occasionally bump into an atomic nucleus, leaving a faint signal in the detector material. Underground detectors, LUX, Panda X, Xenont, buried under kilometers of rock, listened for a WIMP occasionally scattering off an atomic nucleus. None of them found it. Not at the mass range the simplest versions of supersymmetry predicted. Not at the interaction strength the theory calculated. The searches did not find nothing, they found constraints. They mapped out regions of parameter space and confirmed, if a WIMP exists with these properties at these masses, it would have already shown up. It has not shown up. Therefore, if it exists at all, it must have different properties, or a higher mass, or a weaker interaction than the theory most naturally predicted. The simplest versions of the WIMP, the ones that emerged most directly from supersymmetric theory, the ones that matched the dark matter density without fine-tuning, those versions have been searched and are not there. This is a specific kind of failure. The WIMP was not just a dark matter candidate. It was a one-particle solution to multiple problems simultaneously. Find the WIMP, and you confirm supersymmetry. Confirm supersymmetry, and you solve the hierarchy problem. Solve the hierarchy problem, and you fix a structural failure in the Higgs sector. The WIMP was supposed to pull 4 threads at once, none of them came free. The galaxy is still held together by something invisible. That has not changed. But the particle that was supposed to be that something, the elegant, theoretically natural, multiply-motivated candidate that was the leading answer in particle physics for 40 years, has not appeared where the theory said it should. Whatever dark matter is, it has not appeared in the simplest and most natural form many theories expected. Something is there. The galaxy depends on it. But the particle predicted to explain it has not appeared where it should. But what that something is made of, after 40 years of searching, after the most sensitive detection experiments ever built, after the LHC failing to produce WIMPs directly, remains entirely open. That failure arrives alongside the desert problem, alongside the muon anomaly, alongside the W-Boson disagreement, alongside the neutrinos' confirmed forbidden mass. Each one independent. Each one found by separate people looking at separate problems. Each one pointing at the same framework and finding something it cannot explain. But all of those are experimental failures, things the machines searched for and did not find, or measurements that came back wrong. The Standard Model's problems go deeper than experiments. They reach into the mathematics itself. And the first mathematical problem is not a small one. It is the worst numerical failure in the entire history of science. At this point in the story, we need to make a distinction. Everything so far has been experimental. The desert, the LHC searching for particles and not finding them, the muon anomaly, a measurement that will not align with the prediction, the W-Boson dispute, experiments disagreeing with each other, the neutrinos' mass, a confirmed gap in the framework. All of those are things we measured and found wrong. What comes next is different. It is not a measurement that came back wrong, it is a prediction that is wrong, built into the mathematics, present in the equations, not discovered by a machine known for decades, sitting in the open with no solution. Here is the prediction. Quantum field theory, the mathematical framework that underlies the Standard Model, says that empty space is not empty. Even in a perfect vacuum, with every particle removed, quantum mechanics requires that tiny fluctuations keep occurring. Pairs of particles flicker into existence and annihilate almost instantly. This activity fills all of space at all times and carries energy. The theory calculates what that energy should be. The number it produces is enormous, far larger than anything observable, far larger than anything in the universe. The calculation says the energy density of empty space should be close to the maximum value the theory can express. Now, cosmologists measure the actual energy of empty space by studying how the universe expands. The expansion of the universe is driven partly by this vacuum energy. If the vacuum energy were as large as quantum field theory predicts, the universe would have expanded so explosively that no galaxies, stars, or planets could ever have formed. The universe would be cold, empty, and structureless. Instead, the universe looks the way it does. Stars exist. Galaxies exist. You exist. The measured value of the vacuum energy is not enormous. It is extraordinarily small. The ratio between what quantum field theory predicts and what cosmology measures is approximately 10 to the power of 120. Written out, that is a 1 followed by 120 zeros. There is no comparison in ordinary language that conveys the scale of this discrepancy. If every atom in the observable universe were itself a universe, and you counted every atom in every one of those universes, you would still not reach a number close to 10 to the power of 120. Physicists call this the cosmological constant problem. It is not a rounding error. It is not a calculation mistake that anyone found and corrected. It has been known since the 1990s. The most brilliant theoretical physicists in the world have worked on it for decades. No solution exists inside the standard model or the quantum field theory framework that underlies it. Here is what makes this different from every other problem in this documentary. The muon anomaly might be a measurement error. The W-boson conflict might be a systematic error in one of the experiments. The neutrino mass might eventually be explained by a new particle that fits into an extended theory. Those are open questions. The cosmological constant problem is a confirmed failure of the prediction. The measurement is not in question. The universe is expanding at the rate it expands. The value of the vacuum energy is what it is. The prediction from quantum field theory is what it is. The two numbers disagree by a factor that has no precedent in science. There is no fix inside the current framework. Adding a new particle does not solve it. Adjusting a parameter does not solve it. The problem is structural. Mathematics produces a catastrophically wrong answer about one of the most basic properties of the universe, the energy of nothing. The cosmological constant problem is sometimes called the worst prediction in the history of science. That phrase understates it. It is not a bad prediction in the sense of a calculation done hastily or with poor approximations. The calculation is straightforward, using standard quantum field theory that gets everything else right. The result is simply incomprehensibly wrong when compared to what the universe shows us. Every physicist working within this framework works in the shadow of this number. It is the largest single discrepancy between theory and observation in all of science. It has been known for decades. And the best minds in theoretical physics have not found a way to close it. That is the first structural failure. A prediction built into the mathematics itself, not an experimental anomaly that might resolve with more data. A calculational result that is simply, catastrophically wrong. And it is not the only one. The Higgs boson was found in 2012. Its mass was measured. The measurement was correct, and then physicists realized that the mass being correct is itself a problem, because there is no natural reason inside the theory for it to be correct. Finding the Higgs boson in 2012 was a triumph. That part of the story is clean. What happened after was less clean. In quantum field theory, every particle's mass receives corrections from its interactions with other particles. For the Higgs, these corrections should be enormous, pushing its mass roughly 10 to the 17 times higher than what was measured. For the Higgs to sit at its actual value, these corrections must cancel to 1 part in 10 to the 34. This is what physicists call fine-tuning, and fine-tuning is considered a warning sign. Not an impossibility. Nature can produce coincidences, but a sign that something is controlling the system from outside the current theory's view. The history of physics supports this interpretation. When Kepler found that planetary orbits were ellipses with the Sun at one focus, the elliptical shape was not an arbitrary coincidence. It was a consequence of Newton's gravitational force law. When the Balmer series showed that hydrogen emits light at specific regular frequencies, the regularity was not a coincidence. It was a consequence of quantum mechanical energy levels. When the standard model predicted the mass of the W boson and experiments confirmed it, the prediction was not a coincidence. It was a consequence of the electroweak symmetry. Fine-tuning, a situation where two enormous quantities cancel almost perfectly without any theoretical mechanism forcing them to, has consistently in physics indicated either an error in the analysis or a missing piece in the theory. The fine-tuning of the Higgs mass is the most extreme example in the Standard Model. The two enormous quantities that cancel are so large that the cancellation is accurate to 1 part in 10 to the 34th. No physical process known to physics produces coincidences at that level of precision. Something must be making the cancellation happen. The Standard Model does not say what. The most widely studied solution was supersymmetry. In a supersymmetric theory, every known particle has a partner with different spin properties. Crucially, these partners contribute corrections to the Higgs mass that have the opposite sign from the ordinary particles. The cancellation becomes automatic, not a miraculous coincidence, but a consequence of the symmetry structure of the theory. The Higgs mass is protected naturally. For this to work, the partner particles cannot be too heavy. They need to sit close enough in mass to the particles they partner that the cancellation remains effective. The LHC was designed in part to find them. The searches were built around exactly the mass ranges where naturalness required them. No supersymmetric partners were found. Their absence does not prove supersymmetry is wrong. Theoretical modifications can push the partners to higher masses where naturalness becomes less clean, but where they might still exist. The LHC's searches have not covered every possibility. But the mass range where the hierarchy problem is most naturally solved, where the theory provides the most elegant, least fine-tuned answer, that range has been searched. It is empty. So the Higgs sits at its measured mass, in a position that requires a cancellation the Standard Model cannot explain, held in place by a miracle the theory has no mechanism to produce. Finding the Higgs in 2012 answered the question of whether the particle existed. The mass it came with opened a deeper question: why is the mass what it is? And that question has no answer inside the current framework. That is the second structural failure in the mathematics. The third is stranger still. It involves a force that its own equations permit to be asymmetric, and yet is perfectly symmetric. So perfectly symmetric that the precision of the symmetry demands an explanation. And the explanation has been missing for 40 years. The weak nuclear force distinguishes between matter and antimatter, a property called CP violation, measured and confirmed. The strong nuclear force should too. Its equations allow it. The equations that describe the strong force, the framework physicists call quantum chromodynamics, contain a free parameter. This parameter controls whether the strong force respects or violates the symmetry between matter and antimatter. The parameter can take any value across a wide range. Nothing in the theory forces it toward one value or another. It is simply a number that nature chooses, and the theory takes whatever value the experiments reveal. Experiments measure this parameter. The result is extraordinarily small, smaller than 1 part in 10 billion. The strong nuclear force is, to the precision of every measurement ever taken, perfectly symmetric between matter and antimatter. The equations allow asymmetry. They permit the strong force to treat matter differently from antimatter. And yet the strong force does not. Not approximately. Not almost. Perfectly. There is no reason inside the Standard Model for this. The parameter that controls CP violation in the strong force can take any value in a wide range, and it happens to sit almost exactly at 0. The equations do not explain why. The symmetry is exact, and the theory has no mechanism that makes it exact. This is called the strong CP problem, and unlike the hierarchy problem, where at least a theoretical solution exists, even if it has not been confirmed, the strong CP problem sat without even a candidate solution until 1977. That year, 2 physicists named Roberto Pecce and Helen Quinn proposed a solution. if you add a new symmetry to the theory, now called Peccei-Quinn symmetry. The CP violation parameter is no longer a fixed constant. It becomes a dynamic field that evolves until it naturally settles at zero. The parameter stops being arbitrary because the physics drives it toward the symmetric value. The existence of this symmetry predicts a new particle. When the Peccei-Quinn symmetry is broken, a quantum of the associated field is produced. Physicists named it the axion, a word borrowed from a laundry detergent brand because the particle was proposed to clean up a messy theoretical problem. The axion is predicted to be extremely light, far lighter than any known particle, extraordinarily weakly interacting, in effect invisible to conventional detectors, and if it exists, it fills the universe. The axion would be produced in enormous quantities in the early universe and would persist throughout cosmic history, cold and invisible. Its mass and abundance could make it a viable dark matter candidate. The same particle that solves the strong CP problem might also explain the dark matter that holds every galaxy together. Searches for the axion began in the early 1980s. They have not stopped since. Experiments like ADEMX, Haystack, and Abracadabra use superconducting cavities in strong magnetic fields, listening for the faint signal when an axion converts into a microwave photon. Each generation of experiments has been more sensitive than the last. Each has probed mass ranges that previous experiments could not reach. No axion has been found in more than 40 years of searching. But the searches are not finished. The axion's predicted mass spans many orders of magnitude, and current experiments have covered only a portion of the most theoretically motivated range. The next decade of improvements, combining quantum sensing technologies with larger magnets and longer integration times, will push into territory where, if the axion exists at the masses most naturally predicted by the Peccei-Quinn solution, it should finally produce a detectable signal. 40 years is a long time to search for something. But in particle physics, it is not unusual. The Higgs boson was predicted in 1964 and found in 2012. Gravitational waves were predicted by Einstein in 1916 and first detected in 2015. The history of physics is full of particles that were theoretically necessary and experimentally elusive for decades before the technology finally caught up. Its absence does not prove it does not exist. The axion's possible mass range spans many orders of magnitude, and current experiments have covered only a fraction of it. But the fraction they have searched keeps growing without a signal. This is now the situation for the third structural failure. The strong force is perfectly symmetric for no reason the theory can provide. The particle invented to explain that symmetry has been searched for 40 years and has not appeared. There is something worth sitting with in the strong CP problem that is different from the other structural failures. The cosmological constant problem involves a prediction that is wrong by an incomprehensible factor. The hierarchy problem involves a correct answer sitting in an impossible position. The strong CP problem involves perfect precision where the theory expects imprecision. In a certain sense, the strong force is too good. It respects a symmetry so exactly that the precision of its compliance demands explanation. And the compliance has no explanation. It just is. Physicists sometimes describe this as an accidental symmetry, symmetry that appears in the equations without any deeper reason. But accidental symmetries at the level of 1 part in 10 billion are not the kind of thing that appears without reason in nature. The history of physics is full of apparent accidents that turned out to be consequences of deeper structure. And the deeper structure in this case requires the axion, a particle that nature has apparently decided to hide from 4 decades of searches. 3 structural failures in the mathematics of the Standard Model. 3 separate problems. 3 separate missing pieces. No solutions inside the current framework. And alongside all of them, one specific particle keeps showing up in the experimental investigations. Not the structural failures, not the mathematical problems, in the actual measurements, in the data. The same particle. Always at the boundary of what the Standard Model can explain. The muon is not the most common particle in the Standard Model. It is not the most massive, or the most studied in isolation, or the most important to the everyday physics of atoms and light. It is, in most respects, a heavier copy of the electron. Same charge, same interactions, simply more mass. The Standard Model says it should behave identically to the electron in every interaction, adjusted only for the mass difference. This principle is called lepton universality, and the muon has spent the last 25 years making that principle uncomfortable. We already discussed the muon G2, the magnetic moment measurement that persists across 2 machines and 2 decades without resolution, with the added complication that the theoretical prediction itself is under dispute between 2 methods. But that is not the only investigation where the muon keeps appearing. For most of the 2010s, measurements at the LHC-B detector, one of 4 main experiments at the LHC specifically designed to study the decays of particles containing heavy quarks, showed something unexpected. Certain rare decays involving B mesons were producing fewer muons than the Standard Model predicted. In these processes, the decay should produce electrons and muons at in effect the same rate, adjusted only for their mass difference. Instead, muons appeared less frequently than they should. This was called a lepton universality violation, and it grew year by year as more data accumulated. By the late 2010s, the anomaly had reached several sigma of statistical significance. Theoretical papers multiplied, candidate explanations were proposed. The possibility that a new particle, something with specific interactions that affected muons differently from electrons, was influencing the decay became a serious subject of discussion. Then, in late 2022, the LHC-B collaboration published a new and more precise analysis of those same measurements. They called it an improved analysis of the R_K and R_K star ratios. The updated result moved toward the Standard Model prediction. The earlier muon deficit largely disappeared when the analysis was done more carefully, that is, science working correctly. An early pattern, subjected to better analysis, found to be less dramatic than it initially appeared. The muons were not as deficient as earlier data suggested, but sit with what happened during that process for a moment. For nearly a decade, a muon anomaly accumulated, attracted theoretical explanations, motivated dedicated follow-up experiments, and generated hundreds of scientific papers. Then it faded under improved scrutiny, while, at the same time, a separate muon anomaly at Fermilab was being confirmed by a dedicated machine specifically built to check it. The muon keeps appearing. Some appearances are confirmed, some dissolve, but the pattern of appearances is itself unusual. The proton radius is another example. For years, measurements of the proton's size using muonic hydrogen, ordinary hydrogen, where the electron is replaced by a muon, which orbits much closer to the nucleus, returned a smaller value than measurements using ordinary hydrogen. The discrepancy was larger than experimental error could explain. It became known as the proton radius puzzle. Later measurements narrowed the discrepancy significantly. The muonic and electronic values moved closer together as experiments improved. The puzzle did not fully resolve, but it reduced. What it left behind was a lesson. Muon-based measurements sometimes probe physics in ways that electron-based measurements do not, and the discrepancies between them, even when they eventually narrow, can reveal assumptions hidden in the analysis that nobody had examined before. No other particle in the standard model has generated this frequency of unexpected results across this many independent experiments over this long a period of time. The G2 persists after 2 dedicated machines and a final measurement at the design precision. The earlier LHCb anomaly faded, but required nearly a decade of work to resolve. The proton radius raised questions that improved measurements eventually narrowed, but did not entirely close. At some point, the frequency of appearances in the investigation is itself a data point. The muon is not simply wrong in every test. The picture is more careful than that. But no careful investigator dismisses a pattern because individual instances have complicated resolutions. The muon is the most watched particle in physics. It keeps arriving at the boundary of what the standard model can explain. Theorists have proposed specific candidates, leptoquarks that couple quarks and leptons directly, or a new heavy boson coupling more strongly to muons than electrons. Neither has been confirmed. But the proposals are specific and testable. Whether the ultimate answer is one of these proposals or something else entirely, the muon has been the most productive stress test of the standard model in the last 25 years. Every place it appears in the reports is a data point in the investigation. And when you step back from the individual particle and look at the full picture, the muon anomalies, the structural failures, the missing candidates, the confirmed gaps, something becomes clear that was not visible when you were looking at any single problem. The standard model does not have one gap, it has a boundary, and that boundary has been traced from multiple directions. 7 problems. 8 if you count the muon's pattern across experiments as a separate category from the G2 alone. Found by different research communities, in different countries, over different decades, using different machines and different methods and different theoretical frameworks. The desert, a decade of searching at the highest energies ever achieved, finding nothing where the theory said something should be. The muon G2, 2 dedicated machines, 2 decades, a discrepancy that persists alongside a theoretical prediction that 2 independent calculation methods cannot agree on. The W boson mass, the world's best precision measurement experiments, producing incompatible results about one of the fundamental force carriers. The neutrinos mass, a Nobel Prize winning experiment, confirming that the theory's own structure forbids something the universe demonstrably does. Dark matter's missing candidate, the WIMP failing every direct search. Its absence undermining the theoretical framework that most naturally predicted it. The cosmological constant, the energy of empty space predicted wrong by 10 to the 120th power, the largest numerical failure in the history of science. The hierarchy problem, the Higgs boson sitting at a precise mass that requires a cancellation the theory has no mechanism to produce. The strong CP problem, the strong nuclear force exhibiting perfect symmetry with no theoretical reason for that symmetry, and the axiom proposed to explain it missing after 40 years of searching. None of these come from the same team, none of them are versions of each other. The cosmological constant is a failure of quantum field theory's prediction of vacuum energy. The hierarchy problem is a failure of the Higgs sector's natural stability. The strong CP problem is a failure of the strong force to explain its own symmetry. The muon G2 is an experimental measurement of a spin property. The neutrino mass is a confirmed observational fact about a particle's behavior. The W-boson dispute is an experimental conflict between precision instruments. The WIMP absence is a strategic failure of a theoretical prediction to survive experimental search. These are different kinds of failures. They were discovered by people who were not looking for each other's problems. They arrived independently from different directions using different tools, and they all belong to the same framework. Here is the important nuance. These problems do not all point to the same missing piece. The cosmological constant problem may require a completely different type of solution from the hierarchy problem. The strong CP problem and the muon G2 may have no connection to each other at all. Some of the failures are experimental, measurements that came back wrong. Some are mathematical, predictions built into the theory's own equations that are catastrophically off. The categories are different. But that distributed nature of the incompleteness is in a way more unsettling than if all the failures pointed to one place. If there were one clear gap, you could imagine filling it with one clear new particle or one new force. The distributed picture means the framework is incomplete in multiple independent ways, each requiring something different to fix. Think of it this way. Imagine a city built according to a master plan drawn up decades ago. The plan was extraordinary. It predicted where roads would need to go, where buildings would cluster, how utilities would run. For decades, everything built according to that plan worked. The plan felt like it described the city completely. Then, over 30 years, separate departments begin reporting problems. The water engineers find pressure failures in districts the plan said should be well served. The electrical grid develops cascading inefficiencies the plan did not predict. The roads develop bottlenecks at the edges. The telecommunications network has dead zones in areas the plan said should have coverage. Each department investigates independently. Each finds a technical explanation for its specific problem. But when a city planner finally looks at all the reports side by side, a pattern appears. Every failure is located at the same type of place, the boundary between the old planned districts and the newer extensions built after the original plan was completed. The plan was not wrong about the original city, it was incomplete about how the city would grow. The standard model is the original city plan. The boundary failures are what we have been mapping tonight. Not one gap, but the outline of a boundary. The shape of a theory that describes the known and does not describe what lies beyond. Physics has been here before. In the late 19th century, physicists thought the major discoveries were done until special relativity and quantum mechanics arrived. The problems that led there were not obvious catastrophes, they were small anomalies. The standard model's failures look, from the inside, exactly like that. The question changes at this point. Not, what is wrong with the theory? We have mapped that. It is confirmed incomplete from multiple directions. The question is, what is on the other side of the boundary? And the field has specific, testable candidates, not guesses, proposals with predicted properties, predicted masses, predicted interactions, proposals that can be searched for with machines that exist right now. The field is not without answers. It has too many. The problem is not a shortage of ideas, it is an excess of untested ones. When the standard model's boundary became clear enough to map, theorists went to work building proposals for what lies beyond, not guesses. Structured theoretical frameworks, each making specific predictions, each testable in principle, each designed to address one or more of the failures this documentary has been tracking. Supersymmetry is the oldest and most developed candidate. It proposes that every known particle has a heavier partner with different spin properties. The partners of quarks are called squarks. The partners of leptons are called sleptons. In a supersymmetric world, the Higgs mass problem solves itself. The corrections from ordinary particles and their supersymmetric partners cancel naturally, without fine-tuning. The lightest supersymmetric particle, if stable, would behave exactly like dark matter. The LHC found no supersymmetric partners at the energies it searched. The elegant, natural versions of supersymmetry are in serious tension with the data. But the theory survives in modified forms at higher masses, and the high luminosity LHC will push the search further. Sterile neutrinos are a more targeted candidate. They do not interact through the weak force, making them invisible to most detectors. Their existence would solve the neutrino mass problem through the seesaw mechanism, naturally producing the tiny masses we observe. They are being searched for in nuclear reactor experiments and at accelerators. The hints that appeared in some early searches have not solidified into a confirmed signal, but the search continues at greater sensitivity. Axions remain the leading solution to the strong CP problem. 40 years of searching has covered a significant range of the axion's possible properties, but far from all of it. Experiments like ADMX, Haystack, and Abracadabra are now reaching into previously unexplored mass ranges with quantum-limited sensitivity. If the axion exists in the mass range most naturally predicted by the Pecquet-Quinn solution, these experiments are approaching the sensitivity needed to find it. The search is not a long shot. It is a careful process of elimination through increasingly precise territory. Dark photons are another family of candidates. They are hypothetical lightweight particles that mediate a new force operating in a hidden sector, a parallel collection of particles and interactions that barely touches the standard model except through rare quantum portals. A dark photon with the right properties could explain why dark matter was never produced at the LHC and never detected directly. It exists in a sector that barely connects to the particles the machines were designed to produce. None of these has been confirmed. Each is a specific, testable prediction. The situation is a structured search with the right tools. And the tools are being upgraded. The high luminosity LHC will produce roughly 10 times more collisions per second. Rare events where new physics hides will accumulate in samples 10 times larger. Every measurement will sharpen. Whatever is on the other side of the standard model's boundary has specific predicted properties from each of these frameworks. When the high luminosity LHC begins operating, each one will either produce a signal or narrow the remaining space significantly. There is a third possibility worth naming. What if the high luminosity LHC also finds nothing? Not a confirmed signal, and not a resolution of the current anomalies, but simply more desert? More precisely measured emptiness? Physicists discuss this openly. It is a possibility that must be taken seriously. If the high luminosity LHC runs its full program and produces no confirmed new physics, the field will face a deeper crisis than it faced after run 2 of the LHC. The anomalies currently sitting in the data would either have faded or remained at their current statistical levels, below discovery threshold, unresolved. The standard model would have survived its most stringent tests. And the theoretical frameworks built to explain the framework's gaps would be in severe tension with the data. At that point, the discussion would shift to the next generation of machines, the future circular collider, proposed to be more than 3 times the circumference of the current LHC, capable of reaching collision energies many times higher. That machine would take decades to build and cost more than any physics instrument ever constructed. The decision about whether to build it would be made partly on the basis of what the high luminosity LHC finds. But that future is not yet here. the high luminosity LHC has not run. The Run 3 data is being analysed now. The muon G2 result is published, and the theoretical debate continues. The anomalies are live. The searches are active. The next chapter has not been written. Whatever is on the other side of the standard model's boundary has specific predicted properties from each of these frameworks. When the high luminosity LH begins operating, each one will either produce a signal or narrow the remaining space significantly. But there is a deeper question still. Beyond the particles, beyond the experiments, beyond the technical machinery of the search, why does any of this matter? Why should what happens in a tunnel beneath the French-Swiss border change anything about the world above it? Before we reach the machines and the data, there is something you should understand about what is actually at stake in this search. Particle physics discoveries can feel abstract. A muon spinning at the wrong rate, a boson weighing too much, a symmetry that should break but doesn't. These sound like technical problems for specialists in tunnels far underground. Interesting, perhaps, but distant. They are not distant. Every layer of physics understanding in human history has produced changes in the world that nobody predicted when the physics was first discovered. Maxwell's equations produced the electrical grid and wireless communication. Quantum mechanics produced the transistor and every computing device ever built. The Standard Model produced the World Wide Web. Invented at CERN in 1989 to share particle collision data between institutions. New physics beyond the Standard Model would not leave the world unchanged. It never has. But that is not the deepest reason it matters. The deepest reason is this. The Big Bang produced matter and antimatter in equal quantities. This is what the Standard Model predicts. This is what the physics of a hot, symmetric early universe requires. Equal amounts of matter and antimatter created simultaneously, filling the same volume of space. Equal amounts of matter and antimatter in contact with each other annihilate. The process is complete. Every particle meets its antiparticle partner. They convert into radiation. They disappear. What remains is a universe of pure light, cooling and expanding, with no atoms, no chemistry, no stars, no planets, and no observers of any kind. That is what should have happened. Instead, something gave matter a tiny edge. One extra particle of matter for every billion matter-antimatter pairs. The billion pairs annihilated in flashes of radiation that still fill the universe today as the cosmic microwave background. The one extra particle survived. Everything that exists, every star in every galaxy, every atom of every planet, every molecule of every living thing, is made from those 1 in a billion survivors. One extra particle for every billion pairs. The billion pairs annihilated. The one extra survived. You are made of that one. You are here because roughly 14 billion years ago, the universe was not perfectly symmetric. Something broke the symmetry, just barely, just enough. And the excess that resulted is everything. The Standard Model contains CP violation measured in kaon decays in 1964, but the amount it contains is billions of times too small to explain why matter survived. The asymmetry that produced everything requires something the Standard Model does not contain. This is not a small discrepancy. It is a chasm. If you tried to explain the observed matter surplus using only the CP violation the Standard Model provides, you would fall short by a factor that makes all the other discrepancies in this documentary look trivial. Something beyond the Standard Model is responsible for the existence of matter. The thing that exists where the Standard Model's boundary lies, whatever it is, whatever candidates turn out to be correct, connects directly to the question of why there is anything at all. If new CP violation is found in the anomalies being studied, in muon sector processes, in rare meson decays, in precision measurements that probe the edge of the framework, it would be a step toward identifying the source of that asymmetry. Not proof. Not a final answer. A step. But a step toward the most fundamental question physics can ask. Dark matter matters in a similar way. It makes up roughly 27% of the energy content of the universe. It shapes every galaxy's structure. It was the gravitational scaffolding around which the cosmic web of filaments and voids assembled after the Big Bang. Understanding what dark matter is made of, whether it is a sterile neutrino, an axion, a dark photon, or something else, would not just be a scientific answer. It would change how we understand the composition of the universe we live in. The machines at CERN are not searching for abstract numbers. They are searching for the reason existence is possible. And the most important run those machines have ever conducted just ended. In late June 2026, following its final physics run, the Large Hadron Collider was switched off to begin Long Shutdown 3, the major maintenance, consolidation, upgrade and installation program that will prepare CERN for the high luminosity LHC. The beam stopped. The cryogenic cooling systems began their gradual warming. The tunnels, usually occupied only by the hum of equipment, fell quiet. Engineers began entering with maintenance tools, beginning work that will continue for years. This was not a failure, it was a transition. The machine is undergoing a transformation. Inside the tunnel, the superconducting magnets closest to the 4 collision points will be replaced with new ones capable of focusing the proton beams far more tightly. Tighter focus means more protons overlapping in the collision zone per second. More overlapping protons means more collisions. More collisions means more rare events. And rare events are exactly where the standard model is most fragile. The new magnets are made from a different superconducting material than the original ones, niobium tin instead of niobium titanium. Niobium tin can carry higher currents and generate stronger magnetic fields, but it is harder to manufacture and more brittle. Building these magnets required new fabrication techniques developed specifically for this upgrade. Hundreds of them have been produced at facilities across Europe, the Americas, and Asia. The inner tracking detectors at the large experiments are also being rebuilt. Years of intense radiation from billions of collisions have degraded the original detector layers. New silicon tracking systems, more granular and more radiation tolerant, will replace them. The trigger systems, the electronics that decide in microseconds which events to save out of the billions happening every second, are being upgraded with faster processing built around algorithms designed specifically for the higher collision rates. Long Shutdown 3 is scheduled to last until approximately 2029. When the high luminosity LHC begins operations, the collision rate will be approximately 10 times higher than the current machine's design peak. The physics program that the upgrade enables is direct. Every anomaly currently sitting below the 5 sigma discovery threshold will either produce a much stronger signal or be definitively constrained. The high luminosity LHC will sharply increase the number of collisions and improve sensitivity to rare processes. Some anomalies may strengthen, some may fade, some may remain unresolved, especially if the missing physics lies outside the machine's reach. But the precision of every measurement will improve substantially. Yet the most important fact about where physics stands right now is not about what the upgraded machine will do. It is about what the current machine has already done. The data from Run 3, the LHC's final run before Long Shutdown 3, is already recorded. It sits on storage drives at CERN's computing center and at distributed computing facilities in dozens of countries around the world. The Run-3 dataset is the largest the LHC has ever produced. More collisions than in any previous run. More rare events. More precision in exactly the measurements where the standard model is under the most pressure. The anomalies that were active during Run-3, the flavor physics signals, the precision electroweak measurements, the rare decay rates, either grew stronger in that data or they weakened. The result is already determined. The universe showed its hand during Run-3. Physicists are currently reading the data. At Fermilab, the muon G2 collaboration has already released its third and final measurement. The result agrees with the 2021 and 2023 measurements and reaches a precision of 127 parts per billion, better than the experiment's original design goal. But the interpretation still depends on the theoretical prediction, where data-driven and lattice calculations remain part of an active debate. The measurement is as precise as the experiment can make it. The theoretical side now needs to resolve its own disagreement before the physical conclusion can be drawn. Both outcomes are possible. The measurement could turn out to confirm new physics once the theory settles, or the theory could shift and the anomaly could narrow. Both possibilities are live. The final word on the muon G2 anomaly will come not from the experiment, which is done, but from the theoretical physics community finishing its own internal argument. This is one of the rarest and strangest positions in science. The measurement exists. The answer to whether it represents genuine new physics is not in the measurement, it is in the calculation. And the calculation is unresolved. Meanwhile, the Run-3 data sits waiting. Physicists working in shifts at institutions around the world are processing it. The Run-3 data exists. It is being analysed now. Some of it has already produced published results. More results are in the pipeline. Each new result either narrows or widens the space where new physics can hide. The data may already contain the next clue. It may strengthen a pattern, dissolve an anomaly, or narrow the space where new physics can hide. The answer may not arrive as one clean discovery, but the next boundary of the standard model is being measured now. Somewhere in those storage drives, the universe has already given its answer to the questions this documentary has been tracking. The standard model, the most tested theory in history, confirmed wrong in at least one place, incomplete in several others, and facing experimental anomalies in a third category, has been subjected to its most extensive dataset. The result is already there. Either outcome advances the investigation. The question is which direction the data points. The standard model has been tested more than any theory in the history of science. The result is already there. The question is what it says. Picture that chart again. One poster. Every particle ever confirmed, every force ever measured, every fundamental interaction ever tested. The entire menu of what the universe is made of, compressed into a diagram small enough to carry under your arm. That chart is correct about almost everything. It correctly predicted the electron's magnetic moment to 11 decimal places. It correctly described the behavior of particles decades before the machines powerful enough to produce them existed. It correctly explained why atoms hold together, why the sun burns, why light behaves the way it does. For 50 years it passed every test thrown at it, and it is already confirmed wrong about the neutrino. It has no solution for the cosmological constant. It has no natural explanation for the Higgs mass. It cannot explain why its own strong force is symmetric. It cannot explain why matter won after the Big Bang. These are not hidden secrets. Physicists know about all of them. They have known about the neutrino's confirmed mass since 1998. They have known about the cosmological constant problem since the 1990s. They have known about the hierarchy problem since the 1970s. They have known about the strong CP problem for nearly 50 years. The people who work with this framework work inside those known gaps every day. They are not embarrassed by them. They are motivated by them. Because every time a framework in physics has reached its boundary, what came next was not a correction. It was a new layer of understanding. What lies beyond the standard model's boundary will not erase what it got right. It will reveal the standard model was a special case, accurate up to a point, and that at the boundary, something deeper operates. The missing piece, whatever it is, has been leaving marks. In the muon's stubborn disagreement that 2 machines and 2 decades have not resolved. In the W boson's disputed mass that 2 groups of careful scientists cannot reconcile. In the neutrino's forbidden mass that a Nobel Prize-winning experiment confirmed and the framework still has no mechanism to produce. In the silence where the WIMP should have appeared. In the perfect symmetry of the strong force that has no reason to be perfect. In the energy of empty space that is predicted wrong by a factor the human mind cannot picture. Those marks have been mapped. The boundary of the theory has been traced from multiple directions over 30 years. Every prior mapping of a theory's boundary produced something extraordinary on the other side. The boundary of Newtonian mechanics produced special relativity. The boundary of classical physics produced quantum mechanics. The boundary of earlier theories of the atom produced the standard model itself. The boundary of the standard model has been reached and mapped from multiple directions. Something is on the other side. The experiments building now, and the data already recorded, are the first systematic attempt to see what it is. And the machines built to find what lies beyond that boundary have just delivered their most extensive data set. The data is being read now by physicists in Geneva, in Chicago, in Tokyo, in Beijing, in institutions on every inhabited continent. The answers inside that data are not theoretical. They are real. They exist in the measurements that have already been made. Whether the Run-3 data reveals a strengthening pattern, or whether the muon G2's final precision resolves into confirmed new physics or a resolved calculation dispute, or whether the high luminosity LHC in 2029 finds something hiding just at the edge of what the current machine could see, the investigation is not finished. It has never been more structured, more precise, or more focused. The boundary has been mapped. The analyses are in progress. On the other side of this boundary, something is waiting. Something that explains the neutrino's mass. Something that fills the dark matter maps. Something that produced the CP violation that let matter survive. Something that makes the Higgs mass natural and the vacuum energy real. Something the standard model cannot see, but something the experiments are already measuring. Good night.